just taking a step back here, what we've just done is we've identified the fact that a massless photon not only can have a momentum, but that the momentum of that photon is actually inversely related to the wavelength. And it's just quite a simple formula here. And at this point here, this is where we're going to take a level of abstraction into the deep here. And we're going to say, okay, everything we've just done in analyzing this is for a massless particle. Now, let's just, for the hell of it, apply it to a massive particle and see where that gets us. And this is, essentially what de Broglie did. And this is also why, at first, his hypothesis was not accepted in the physics community, because it seems like he's using analysis for one situation and applying it to another. But the rationale for this is that we've already seen that particles do have a wave-like nature. So really, at a deeper level, what he's doing is saying, now that we identify that they both can have similar natures, why should we use one set of mathematics for one thing and another set of mathematics for another, when ultimately it's almost like they are the same? So let's go ahead and just take this and let's say, let's project it onto massive particles, and let's see where that goes. And to be clear, we're not going to rederive Einstein's energy equation. We're still going to leave m equal to 0 in his equation, but we're also going to accept this to be true, and we're going to arbitrarily add an m later on. So, specifically, we're going to say that you have some particle with a mass m, and we know classically that the particle will behave like that. So classically, if it's going with a speed v, p, of course, equals mv. But now if we use this exact same thought process and let's do it. Let's imagine that maybe there's a chance when those massive particles, for example, electrons, as we've seen in the double slit experiment, we see that very definitely some of the results of the double slit experiment indicate that these particles do in fact behave like waves. Because specifically we saw that there were very definite interference patterns, which implies directly that there is some sort of cancellation that can only occur if there is some sort of a phase change as the particles move forward. Again, I realize what I'm saying is complicated, and this is why actually the beauty of lectures on video is that you can rewatch it. But what I'm saying is that photons move forward, they propagate forward with a sinusoidal phase, and that's what de Broglie said particles might also do. Particles might also move forward with effectively a wavelength, the same way that photons do. And again, he's not saying that they move up and down, but what he's saying is that if there is a phase associated with photons, why shouldn't there be a phase associated with electrons, for example? So we're now going to draw this like this. So the massive particle can move with a velocity v, but if photons have some phase associated with them with a given wavelength, let's assume so for an electron. And by the way, I am talking about electrons here. It applies for any massive particle, but the electrons are kind of the easiest thing to visualize. So if particles have a wave associated with them, or if they have a wave nature, I should say, associated with them, the analysis we've just done should predict that wavelength lambda, when we do some basic analysis here, we can predict exactly what wavelength that should be. The wave of that particle, using the same analysis, should simply be whatever that constant is, which we have experimentally measured, divided by the momentum. And I will make that correction now using our classical analog. H over P, or H over mv. And this is exactly what is called the de Broglie wavelength. I'll write it right here. And one more thing, he was, what is it, Belgian, I think, and it's properly pronounced de Broglie, like Broylie. It looks like de Broglie, but that is not in fact how it's pronounced, and I think that's exactly how I pronounced it for the first year as well. So, this is what we call the de Broglie wavelength. And I want to do a quick example with this, and this is kind of a fun thing to do. So we can do it for an electron. And we can find a given length of electron. So I want to do kind of an example here. Imagining an electron traveling at a relativistic velocity. And there's, because that applies because, as you recall, the whole thing that we started this off with was assuming Einstein's relativistic energy to be true. So let's imagine you have some electron traveling at 90% the speed of light. Let's say 10% just to make the math a little bit easier. Example, electron. So if you have an electron traveling at 10% the speed of light, what is the de Broglie wavelength? And I mean, these types of questions really are not that inordinately difficult to answer because you literally plug 3 things in. So, the questions don't get much simpler than this, but I just want to be very clear on like what wavelengths we're talking about here. So the mass of the electron, as you may recall, is, and I'm gonna estimate to orders of magnitude. So specifically, I'm just going to approximate this as, now these are some figures that essentially, eventually you should probably at least know on the order of magnitude. The mass of the electron is on the order of 10 to the minus 31st kilograms. The Planck's constant is of the order of 10 to the minus 34 joule seconds. And then 0.1 C is of the order of 10 to the 7 meters per second. Yeah. Okay, so the one correction I'll make, it's 9 times 10 to the minus 31st, so I'm going to round that to 10 to the minus 30th. This is actually 6 times 10 to the minus 34, so you can round to 10 to the minus 33 if you want. Both of those actually cancel themselves out, so neither of that really matters. But the whole point is that when you do this analysis to just order of magnitude estimates, the wavelength that you get out, and by the way, when we're just doing order of magnitude analysis, that's really kind of the symbol that we use. There's kind of a joke in cosmology that there's only really 2 numbers. Only 2 things you keep when you do this analysis. You only keep the number pi and the number 10 to the. So we're only keeping the number 10 to the for this. So in this case here, we're simply going to estimate this as h over mv, or in this case, we're going to have 10 to the minus 33 divided by 10 to the minus 30 divided by 10 to the 7. Sorry, 10 to the positive 7. And these are all SI here, so we can be quite confident that the units will work out to be meters. And so when you do this here, this will end up being on the order of 10 to the 4. And I have forgotten how to subtract, well, I've forgotten how to, subtract positive numbers is literally what it is. That's the same thing, and I'm embarrassed that I have to write this out for myself, but that's the same thing as 10 to the minus 34 times 10 to the positive 30 times 10 to the minus 7. What I did before in my mind was I added that 7 rather than subtracted that. So by the second grade laws of exponential analysis or multiplication, that's the same thing as 10 to the minus 34 plus 30 minus 7. So pretty clearly, this is 10 to the minus 11, and I am so much happier about that. And that is in fact meters, because that's the order of things that we should be looking at. So everything I just described was just completely BS. But yeah, thank you again for that. So that's important, because when we do our next step here, if we recognize that an electron that has a mildly relativistic velocity, if de Broglie was correct, it would imply that the electron's wavelength would be, and we're going to find this out very shortly, on the scale of about an angstrom. And as you recall from things you may not have learned, one angstrom is it's basically what we use to measure nuclear particles or the nucleus of an atom. I'm sorry, no, that's a Fermi. A Fermi is 10 to the minus 15. 1 angstrom is, we write that as 10 to the minus 10 meters. That's what we define an angstrom to be. And we write that as 1 a circle. Angstrom, by presumption, was, I think that's Swedish or Finnish or what's the other one? Norwegian, one of those Scandinavian things. But an angstrom is the size about of an atom. And so this is a little bit smaller than an atom, and that's exactly what we want. Good, I feel that much happier about life yet. So, anyway. So we've analyzed this, and the electron does in fact have a wavelength on the order of an angstrom. So, there we are. And I'm already taking my warning into practice here. I guarantee we're going to do something wrong. We've just done that. So, very good. So, there's other fun examples that we can do with this, and the one that I think I'll assign as homework is, what is the de Broglie wavelength of a baseball thrown at 100 miles an hour? For what it's worth, baseballs have a mass of something like 140 grams, and 100 miles an hour, you put into SI units. You find that when you do this, and I'll let you get the exact numbers, but on macroscopic terms, when we're dealing with macroscopic objects, and we try to apply this, the de Broglie wavelength of that is going to be something like 10 to the minus 16 meters. So when we talk about the de Broglie wavelength for objects, if we're looking at large scales, it is entirely possible that when I walk forwards, I might have a de Broglie wavelength associated with me, but my de Broglie wavelength is going to be so minutely small that it is simply unmeasurable with current equipment. But it only becomes important on small scales like this, on quantum scales. And in fact, I wish I would have done that baseball example here, because it is a little bit easier to visualize, and it gives kind of an interesting result that those wavelengths do become incredibly tiny.